We have a bar magnet here. As you can see, the north pole is given in red color and south pole is in green color. And we have got a small compass here, of course. Okay. And like we just want to trace the path of the direction of magnetic field, and that is what we mean by a line of force. Okay, if you have an isolated north pole, normally it doesn't exist, it is only a hypothetical consideration, and if you leave the north pole here, it is repelled by the north pole and attracted by the south pole, and the resultant path is traced actually. So if there is a north pole which is left here, it just moves along that line, and that's called the line of force. So we can draw a number of lines of force. Okay, and see, in fact, it is the direction of magnetic field. See how a compass is moving, we just have to trace the path. As simple as that. That's what we are doing. It always starts from the north pole and moves towards the south pole. Okay, and we mark all these lines of force, and the lines of force do not intersect, because at the point of intersection we get a question of the direction of the magnetic field. So there is no confusion for that. Therefore, lines of force do not intersect. And the point that should be remembered here is lines of force we are drawing from north pole to south pole, and within the magnet you can see it is exactly the opposite. It is coming from south to north. It's a closed loop. Any line of force, of course, we are considering it's a closed loop, and therefore lines of force start from the north pole and moves towards the south pole outside the magnet, and well within the magnet it is exactly the opposite direction. Okay, and something interesting we can do here, you just look at the direction of this magnetic field. If I clear all the lines and if I turn the magnet, suppose this is south pole now and this is north pole, I again can identify the direction. The same you can find from north to south. Okay, and we have turned the magnet and we are trying to draw the lines of force once again. And this is how we have the lines of force. In fact, the lines of force are too close to each other when you take near the magnet, and when you move away from the magnet, the lines of force are far away from each other, and therefore the number of lines passing through a unit area, you call it flux density. Okay, the flux density is more here at the poles. So how do we understand this actually? The number of lines, the number of lines which are passing per unit area, you just measure it in terms of Webers per square meter, and that's more here, because there is all the lines of force are too close to each other here, and therefore my point here is the flux density is more here. Therefore, magnetic field induction is said to be very strong at the poles, and therefore the magnetic field induction is strong at the poles, but the lateral magnetism is not that significant, it is weak. And this is how we draw the lines of force, and we try to understand the flux density, and we have identified that it's maximum at the poles and minimum on the sides. And in fact, this also can be measured using a field meter. You can measure, of course, in Gauss units how much of field intensity you got at that point.